team presentation for Team 12. This was Rianna Jawa, Timothy Lackie, and Xudong Liu. The overall goal of our project was to find the locations of 3 different colored blocks, red, green, and blue, and carry them back to their flags. So Rover 1's job was to map the arena, create a map of it, and find the shortest path that would take all the objects back to their flags. And Rover 2's job was to go up to the blocks, use the arm to grab them, and bring them back to the flags. And each block was supposed to be placed next to its flag corresponding to the same color. For this rover, we chose the VL53L0X distance sensor because it's very accurate, and it has range between 10 and 1000 millimeters. Unfortunately, it uses I2C communication, so we ran into issues trying to get that to work. First of all, I had to port the ADA Fruit code from the ADA Fruit website into my project, which took a little while because it had to be converted from Arduino to C. And once I did that, I was running into issues with the arbitration loss. So it would work for a little bit, and then it would stop working, and I couldn't figure out how to fix it. Eventually, one of the TAs figured out that I was needing to shut down the sensor, so I connected the shutdown pin to one of the GPIO pins and was able to get it to restart that way. And after that, that code was just inserted wherever the sensor failed, and it decided to start working. But by the time that happened, it was already late in the semester, and I didn't have much time to work on the project beyond that. As far as accuracy is concerned, the sensor is very accurate. It can detect objects within 1 centimeter, and it's very reliable now, and because even if it fails, it can be restarted. And it's robust because it works with the PixieCam, and is also very accurate, as mentioned before. So for the sorting rover and for the mapping rover, we needed to have a way to detect the color of the blocks and flags. So we used the Pixie 2, which is an upgraded version of the PixieCam, and we needed to detect red, green, and blue. And so I set up the color detection in Piximon and set the sensitivity so that it would be most optimal for our blocks. It turned out to be sensitive to a range of colors, but unfortunately in certain lighting conditions it wasn't as good as you might have seen in the first part of the video. The Pixicam does use UART, which was very convenient for setting up, so once the code was ported I didn't really have to change much to get it to work.
My component involved using the Pixicam to detect the color of the blocks, as well as creating an algorithm that calculates the order that the block should be picked up in. The Pixicam was able to communicate with the PIC using UART, and when detecting a colored object, it would send a series of bytes about this object, and one of those bytes being the signature number, which referred to the color of the block. So this is how I would pick up the color of the block. The Pixicam in my design was not very robust, as it was not able to pick up the colors, which were red, green, and blue, under different lighting environments. So if it was on the surface of a table with good lighting, it was able to be picked up when it was calibrated under that lighting. But if you had put it under the table, it would have a little trouble getting the color. You could, in Piximon, which is the software to recalibrate and configure the Pixicam, you could adjust how much of a color it sees, the range of it, which made it a little bit better, but sometimes it would pick up colors that were not that color, so it was very sensitive to lighting, which made it hard to be robust. But it was able, in our requirements, the Pixicam had to pick up the color of the block from about 1 to 5 centimeters away from the rover, which it was able to do, of course, under the right lighting conditions. Again, under the right lighting conditions, the Pixicam was very reliable, and it would be able to send the correct color every time to the server. It also did not pick up other blocks that were surrounding this one block because of the way that it was mounted, which is seen in this picture. It's mounted like above the block, so if it stops in front of the block, it can still see that block even from 5 centimeters away, which will only get like a little bit of the block. Will still see that color and pick up that color and send it to the server. My piece of pathing was to get the order of the blocks that they needed to be picked up in. So my pick would get from the server the color of the blocks and their coordinates of each block, and I wrote a simple algorithm that would take in all these inputs and figure out which block to pick up first, second, and third based on where they are. As you can see in this picture, we had them set up in columns, so these two blocks are in the first column, so it would make sense to pick up the blue block first, and then the red block, and then the green blocks third. So my algorithm made sure that it would go in that order based on what column they are in and in what order in that column they are in. This was able to be robust with errors in block coordinates, so I did it with errors of 5 centimeters since our columns were set 15 centimeters, 35 centimeters, and 55 centimeters, but if the other pick were to get a coordinate that was an X coordinate that was a little off, I adjusted for error of about 5 centimeters, and based on my test cases, it was pretty reliable. I put in as many different combinations as I could, so those all worked correctly and were sent to the server correctly.
Let me introduce the robot arm works to you. In our group design, we use a 4DOF robot arm which supports stretch, rotate, and grab. It is satisfied the requirements of drop and pick in hardware part. PWM control is used to control the arm in our design. The servo of arm is controlled directly with PWM signal. PWM signal is a communication method that includes information into percentage of the pulse being high or low. PWM signal control is reliable, since it uses a separated timer to calculate the duty cycle. Also, PWM signal has a high precision to control device. It is because the PWM control method could entirely control the every single cycle. Also, we use a shape distance sensor for our design. ARM uses a sensor to generate a distance data to count the physical distance between ARM and the pick drop objects. For communication parts, the ARM control has two communication parts. The first part of communicate is communicate with the server to establish a pick and drop task. ARM pick asks server to send the drop and pick tasks from the database. If task received by the ARM pick, ARM do the pick or drop tasks. If no drop pick tasks passed by the server, ARM pick should keep asking the server until they receive the task. The second part is communicate with the sensor to ensure the distance between ARM and the objects. Sensor can send the detected distance data to the ARM pick. Once the ARM pick received the sensor data, it should estimate the data distance is acceptable for ARM to pick or drop. If distance is acceptable and the task is received, ARM going to work. For the limitation of ARM design, there are three limitations. The first limitation is the reliability of ARM communication system is weak, since there is no testing for data sent and received for ARM pick. The second limitation is the sensor data is not satisfied, because the rover and ARM going to shake when they work. Hence, the data of sensor is changed in a range every time. The third limitation is ARM grabber cannot work perfectly every time. It is too small. Thus, every time when grabber works, it needs a high rate to precision between ARM and objects. It is going to fall pick task if the error of distance is more than 2 centimeters.